Bismillahirrahmanirrahim. Now we will talk about the exercises we want to do for this chapter. So let's say exercises. Number 1A is prove that the root 3 is irrational. And B is prove that there are no rationals R, S such that under root 3 is R plus S into under root 3. Okay. Now, to show this, prove this, A we can do by contradiction. By contradiction, suppose under root 3 is rational. So under root 3 can be written as m over n, where m and n are integers and m and n are in lowest terms. Okay. Now squaring, by squaring, we get m square is 3n square. Thus, m square is a multiple of 3. And so m is multiple of 3. We have proved this statement before. This means m can be written as 3 into k for some integer k. Then 3n square is m square, which is 9k square. So n square is 3k square. Therefore, n square is a multiple of 3. Hence, so is n. We have shown that both m and n are multiples of 3, but m over n is in lowest terms in the assumption. So this is a contradiction. Therefore, under root 3 is irrational. Fact. Part B is prove that there are no rationals such that under root 3 can be written in this form. And to do that, let's say part B, you can also do this by contradiction. By suppose under root 3 can be written as r plus s into under root 2 with r comma s from rationals, and by squaring we get 3 is r square plus 2 s square plus 2 rs under root 2. Now if r into s is not 0, this gives under root 2 is equals to 3 minus r square minus 2 s square over 2 rs. Since r comma s are rationals, this implies that under root 2 is rational, which is a contradiction. Hence, r product of rs is 0. If s is 0, then r square is 3. So r is under root 3, contradicting the fact that under root 3 is irrational by a. But under root 3 is irrational by part A. Therefore, r is 0 and 3 is 2s square. Writing s is equals to m over n in lowest terms. We have three n square is 2m square. Now, by proposition 2.3, we show by proposition 3, we know that m and n must both be even, which is a contradiction. Hence, under root 3 cannot be written as r plus s into under root 2. Perfect. Now, exercise number 2 is prove or disprove. For the following statements, for following statements, either or give counter example. Statement A is for A comma B in rationals, AB is in rational. Statement B is for A comma B is irrationals, AB is irrational. C is the product of two rationals is always rational. And D is the product of a non-zero rational and an rational is always irrational. Now, solve this. Let's say part A says that for A comma B in irrational numbers, AB is an irrational number. So this is true. Let's say if X is M over N and Y is P over Q, and so X comma Y is M P over N Q is also in irrationals. Part B is for two irrationals, product is irrational, and this is false. How? For a counter example, take the rationals. Let's take the irrational number under root 2 and minus 2 are irrationals. Then under root 2 cross minus under root 2 is minus 2. which is a rational. So number 3, C, is the product of two irrationals is always rational, which is again false. Not always rational, sometimes rational, by B. So the product of two irrationals, let's take the rational under root 2 and 1 plus under root 2 is then their product is under root 2 plus 2, which is irrational. Perfect. Part D is the product of a non-zero rational and an irrational is always irrational. And this is true. So prove it by contradiction. Suppose there is a rational A not zero and an irrational B such that C is their product, which is rational. Okay. Then B can be written as C over A. And since A and C are rational, this implies that B is rational. Which is a contradiction. So for a non-negative rational and an irrational, the product is always irrational. Example size 3 is prove that if n is any positive integer, then under root n plus under root 2 is rational. Now, by contradiction, let alpha is under root 2 plus under root n, and suppose alpha is rational, then alpha minus under root 2 is under root n. Square both sides, we will get alpha square minus 2, alpha square plus 2 minus 2 alpha under root 2 is n. So 2 alpha under root 2 is alpha square plus 2 minus n. Since clearly alpha is non-zero, we can divide through by 2 alpha to get. Then divide by 2 alpha, we will get 2 alpha under root 2 divided by 2 alpha, and alpha square plus 2 minus n divided by 2 alpha, we will get under root 2 is alpha square plus 2 minus n divided by 2 alpha. Now is alpha is rational. This implies that under root 2 is rational, which is a contradiction. Hence, alpha is irrational. Hence, alpha is rational. The final exercise, number 4, says that find n given that both n and root n minus 2 plus under root n plus 2 are positive integers. Okay, let's find n. So let an is under root n minus 2 plus under root n plus 2. Then square of this is square of an is n minus 2 plus n plus 2 plus 2 into under root n minus 2 n plus 2, and this is equals to 2n plus 2 into n square minus 4, right? We are given that an is an integer. We know that an is an integer. This implies n square minus 4 is rational. This means that n square minus 4 must be a perfect square. Perfect square, i.e. n square minus 4 is equals to some m square for m to be an integer. Then n square minus m square is 4. And starting a list of squares. So the squares are 0, 1, 4, 9, 16, 25. We see that the only way two squares can differ by 4 is to have n square is 4, m square is 0. So the only solution to n square minus m square is equals to 4 is if we take n square is 4 and m square is 0. Hence, n is 2, so an is 2. The end. Perfect. Thanks so much. This was chapter 2, and after this, we will talk about chapter 3, which is decimals. And in that chapter, that we will see how we use decimals to learn real numbers, and how we can write every real number as a decimal number. And there are some other ways to write the real numbers. Okay. See you in the next lecture.